Hello everyone, I'm Bo from Communication University of China. I'll be presenting a hybrid receiver-side congestion control scheme for web real-time communication. This is a joint work with my advisor Professor Yuan Zhang and my schoolmates Size, Zipeng, and Yu Hong. Firstly, I'm going to give an overview of a typical WebRTC transmitting session. For a WebRTC session, a media stream is first compressed and then packetized to an RTP packet stream at the sender side. At every decision-making interval, the receiver-side controller estimates bandwidth based on a set of metrics measured from received RTP packets. Afterwards, the receiver sends the bandwidth estimate back to the sender via RTCP packets, allowing the sender-side controller to decide the sending rate. In the grand challenge, the bandwidth estimate is fully decided by the receiver-side controller, and the trace-based environment GIM simulated a WebRTC session, allowing us to train and test our model. Before talking about the model, let's focus on the challenge of designing a congestion control scheme for web real-time communication. As shown in this figure, the objective of congestion control is to keep network links operating at the optimal point where in-flight data equals to BGP. By measuring bottleneck bandwidth and propagation delay abide by the uncertainty principle. Existing congestion control schemes for loss-based TCP are mainly based on filling and draining logics to address the problem. But WebRTC apps have stricter requirements on latency than loss-based TCP network scenarios, while still expect high-quality media delivery. It treats the excessively delayed packets as losses, which may bring severe damage to media quality. Therefore, most congestion control schemes designed for TCP are not suitable for WebRTC. To meet real-time requirement, existing heuristic schemes estimate the bandwidth based on a fixed and robust model that can hardly adapt to all network conditions. Learning-based schemes commonly employ deep neural network to generate bandwidth estimate. As a result, they have potentially better performance but are not robust enough. Recently, Abashlo and others have proposed an approach to combine heuristic congestion control schemes and deep reinforcement learning techniques, namely ORCA. It achieves consistent high performance in different TCP networks. Inspired by ORCA, we propose HRCC. We hope the idea of combining both worlds could be migrated to WebRTC. The framework includes two components. First, we implement a receiver-side version of GCC as the heuristic scheme. In our experiments, we noticed that the heuristic scheme decreases its estimation quickly to a sudden bandwidth drop, or a high loss rate, but increases estimation slowly to sudden bandwidth rising, which means it tends to underutilize link capacity when the network suddenly got better or just highly fluctuating. Based on this feature, we implement an RL agent that periodically tunes the heuristic scheme's output estimate based on its observation on network link. By combining two methods, HRCC aims to achieve the robustness of classic heuristic schemes and adaptability of learning-based schemes at the same time. The workflow of HRCC is quite simple. With received RTP packets, the heuristic scheme takes the related statistics from the last decision-making intervals as inputs, and generates bandwidth estimation and bandwidth usage state. Afterwards, the state generator takes states mentioned above to generate state input for the RL agent. At the end of every guide interval, the RL agent outputs a gain coefficient to tune bandwidth estimate. Let's take a closer look at the control logic of HRCC as distinguish the relation between guide interval and decision-making interval. At the end of every decision-making interval, which is 200 milliseconds in this work, the heuristic scheme takes the statistics from arrived RTP packets and output a bandwidth estimate. We treat 4 decision-making intervals as a guide interval. The RL agent output a gain coefficient based on the observation of last 10 decision-making intervals at every end of guide interval. Now we focus on the key modules of HRCC. First, the heuristic CC scheme. It consists of 2 controllers. The loss-based controller calculates the packet loss rate based on the incoming RTP packets. In simple terms, the loss-based controller tunes down the bandwidth estimate when detecting higher packet loss rate and tunes up the bandwidth estimate in lower packet loss cases. And the delay-based controller calculates the delay gradient according to the received RTP packets and decide the trend of delay change and decide bandwidth estimate based on the trend line of delay change. The heuristic scheme takes the minimum value of the two controllers as its final bandwidth estimate. Now we introduce the design of the RL agent. We adopt convolution layers to extract the sequence features and Foley connection layers to encode the gain coefficient policy. For training algorithm, we choose PPO algorithm to train the agent. After every step of receiving RTP packets, the RL agent takes a 6-dimension vector ST. The state vector includes the measurements of the receiving rate, delay, packet loss rate, bandwidth predictions, the most current bandwidth estimation given by HRCC, the cost overuse for the last 10 decision-making intervals, and the time so far since last overuse for the last 10 decision-making intervals. The more detailed information about the HRCC modules can be found in the paper. Now I'm going to give the simulation test results. To show the performance of HRCC, we train a Foley RL-based bandwidth estimator with a structure similar to the RL agent of HRCC. We remove the state information given by the heuristic scheme from state input. It outputs a gain coefficient between 0.5 and 2 to tune the previous bandwidth estimate. We conduct the simulations under 100 network traces to compare the hybrid scheme with both of its individual components, each lasting 100 seconds. The average bandwidth of these traces ranges from 500 kilobit per second to 7 megabit per second, while 25% of them specifying 1% to 10% packet loss rate. As provided in this table, HRCC achieves the highest bandwidth utilization with similar delay and loss performance compared with the Foley heuristic scheme, and outperforms the other two schemes on overall performance. And now I'm going to give 3 specific test cases to take a glimpse of the performance of HRCC. These figures show 2 cases of running simulations under different traces without random loss. As you can see in the left figure, in relatively stable conditions, the Foley RL-based scheme performs well enough. However, in the right figure, the Foley RL version lacks constraints on bandwidth estimate under the other traces that are completely different from the training data. The estimated bandwidth is totally off the trail and causes fatal fluctuations of queuing delay. Furthermore, we evaluate the performance of the 3 schemes in bad network environments with random loss rates. As we can see, the Foley heuristic scheme cannot reach the available bandwidth with its loss-based mechanism, while the Foley RL-based scheme causes extremely high queuing delay, though achieves better bandwidth utilization. In this case, HRCC reaches the best compromise. By catching a glimpse of the 3 cases, we may see that HRCC realizes a more robust performance than the Foley RL-based scheme and achieves higher bandwidth utilization than the Foley heuristic scheme. As a summary, HRCC outperforms both of its individual components on bandwidth utilization and overall QoE. In the following studies, first, there's the latest research shows that by interpreting deep learning-based models using decision tree method, the control logic behind the DNN could be dug out. In our case, we may find out why HRCC tunes in such way, and perhaps improve it in a more precise way. Besides, overweight model could bring dramatic decision delay, and that's not tolerable for RTC. Transferring RL model into a decision tree may efficiently address the problem and make the model more applicable. Second, in actual application scenarios, there are non-negligible propagation delays for receiver-side estimation sending back to the sender. So, the feedback latency should be considered for deciding sender-side sending rate. We will work on that sender-side logic later. With that, thanks for your attention.